Good morning, everyone. So, there's my slide. Good. So, several of the speakers yesterday talked about superconductivity, so that seems to be something which is important. Also, several of them mentioned the word qubit. So, what I will do now is I will put these two things together, and I will talk about superconducting qubits, because that's what we're using to try to build a quantum computer. And so there's one effort here at Chalmers to build a quantum computer, but there's also a European effort. So Andreas Wallraff, who's the next speaker, we're collaborating within Europe to help each other to build quantum computers. So I will start by telling you what are the building blocks of quantum computers. And then Andreas will take it from there. So this is the outline of my talk. I will talk a little bit about quantum revolutions. How does this come about that we now think that we can build quantum computers? Then I will talk about the superconducting qubit in itself. So I say something about superconductivity and how these things act like artificial atoms. And I will show you two experiments where we use these superconducting qubits as artificial atoms. So you will see a little bit how they work. And then I will say a few words about how you start to work towards a quantum computer and how you couple these qubits together. So, good. I think you all know about the first quantum revolution. The first quantum revolution gave us the transistor and the laser. And this is, of course, what gave us the IT revolution, which you all have in your pockets and you use every day. And you really needed quantum physics to make transistors and make lasers and things like that. But now we're entering the second quantum revolution. And I seem to be okay. And the second quantum revolution was really pioneered by these two persons, David Wineland and Serge Haroche. So in 2012, they got the Nobel Prize in Physics for being able to control quantum systems accurately. And this is what has enabled this second quantum revolution, where we can really harness quantum physics and use quantum physics to do something useful. So, and if you encode information in these quantum systems, we call it a qubit. And quantum technology, so by quantum technology, we mean exploiting the elements of quantum physics. And so there are things that you have heard about yesterday, like superposition, entanglement. There's also something called squeezing. So these are inherent quantum phenomena that you can use to do something useful. So just a few words, and this was alluded to yesterday also. What is the power of a quantum computer? And I'll try to explain that to you. So, you know, if you have an ordinary bit, that can be either 0 or 1. But if you have a qubit, it can be both 0 and 1 at the same time. This is what we call superposition. And so this sounds good, right? But if we then couple more of these systems together, more qubits together, then this grows exponentially. So, you know, if you have just 2 qubits, you can, of course, represent 4 different numbers: 0, 0, 0, 1, 1, 0, and 1, 1. That's 4 numbers, right? And if you have 4 qubits, you can do 16 different numbers. And in general, if you have n qubits, you can represent 2 to the n numbers. And this is extremely powerful. So if you have 300 qubits, that means you can represent 10 to the 100 states. 10 to the 100 numbers simultaneously. So if you then can do some manipulation on this quantum register, you can say that you do a calculation on all these numbers simultaneously. So there's a massive parallelism in quantum computing. There's certain problems because when you then read out, you essentially only get one of these answers. But there are algorithms that allow you to extract useful information from the fact that you have all these calculations at the same time. And so just to point that out, 10 to the 100 is much more than there are particles in the universe. So even if you collected all the particles in the universe and built your own hard disk where every particle represented a bit, then you could not store as much information as you could handle with 300 qubits. That's amazing, isn't it? So in October, like just 2 months ago, Google came out and announced that they had reached something called quantum supremacy. How many of you have heard about that? Okay, quite many of you. Good. So in their they had made a quantum computer out of 53 qubits. And they use superconducting qubits. So what I'm going to tell you now is what are those qubits that were in the Google quantum processor, and how do they work? This remote doesn't work. Yeah, we should switch to quantum remotes. OK, so here you see a superconducting qubit. The light gray here is aluminum. The dark gray is the silicon on which this circuit is sitting. So this is a superconducting circuit. I'll come to superconductivity in a minute. And you see that this is essentially a capacitance. And then there's a small component up here that does all the trick. The whole circuit is like 0.5 millimeter across. But this little circuit that does the trick is just 100 by 100 nanometers. And this can now act like an artificial atom. And in particular, it can have, it behaves quantum mechanical, and it can show superpositions. This was not obvious 30 years ago, that circuits can behave quantum mechanically. They're so big, but still they can behave quantum mechanically. So a few words about superconductivity. So superconductivity is something that happens in metals when you cool down a metal and measure the resistance of it. You see that at some point, at some temperature, the resistance drops to 0. That's superconductivity. There's also, so this is the most notable property of a superconductor. There's also another property, which is that it expels magnetic fields, and that allows you to levitate a magnet on top of a superconductor. So it actually can levitate above, and you can see here that it just floats in space. You may think that superconductivity is a rare phenomena, but actually, if you look at the periodic table, the blue elements you see here are all become superconducting at some temperature. The green ones become superconducting if you apply a pressure. So in fact, superconductivity is a very usual phenomena if you're at low enough temperatures. So now, how do we put superconductors into, do we make them into qubits? So first I want to discuss, the basic elements that you know about from electricity, the capacitor. So I remind you that the current in a capacitor is given by the capacitance times the derivative of the voltage. And conversely, in an inductor, the voltage is given by the inductance times the derivative of the current. Now, and so you make these type of components out of superconductors, and that means you have no loss. So if you lose energy, you also lose information. So this is an important part, that you want to have something which is lossless. So to build an actual qubit, a superconducting qubit, you start out by just putting these together here in a resonance circuit. So this is a resonance circuit that will oscillate at some frequency. And so charge will be on the capacitor, and it will go through the inductor, go here, and then it'll go back again. And this will repeat itself many, many times. So typical frequencies are 5 gigahertz, the same frequencies that you have in your cell phones and Wi-Fi's. But now if you have a circuit like this, the energy spectrum is equidistant. It means that if you supply energy and excite from this state 0 to 1 here, you can then continue with the same energy to go to 2 and to 3 and so on. This is what's called a harmonic oscillator. But now, if we want to make this like an atom, we need a nonlinearity. And this is where this component comes in. This here is called a Josephson Junction. This is a nonlinear element that acts like an inductor. But it's so nonlinear so that when you put in a single excitation, a quanta of excitation into this oscillator, just that first oscillation, or first quanta, changes the value of the inductance. So then when you, and that changes the resonance frequency of this, so that the next quanta you want to put in, you have to put in at a different frequency. And that's what you see here. So you get a non-equidistant energy level spacing. And so now, if you apply radiation to this with a precise frequency that corresponds to this level splitting, you can go up to this, but then you don't get further because then there's no levels that you can go to. And so if you concentrate on only the 2 lowest levels, then we call this a qubit. If we also include the higher levels, this is precisely like an atom. So we call this an artificial atom. So I'm actually going to skip that and go to this one. So in this person here is Brian Josephson. When he was 26 years old, he figured out what happens in a system where you have a superconductor on one side, an insulating barrier, and then a superconductor on the other side. So he derived these very famous equations, or these Josephson relations, that tell you how current and voltage depend on the properties of the superconductor. And the interesting thing is that if you combine these two expressions, you can see that this element looks like an inductance. It actually acts like a non-linear inductance. And that is precisely what we needed for the resonance circuit I had before. So a Josephson junction is approximately equal to inductance. It's a non-linear inductance. And now you can do one more trick, and that is to put 2 of these in parallel. And without going into details, what happens then is that you can actually make a tunable inductance. So by putting magnetic flux in this loop here, you can actually tune the inductance, and therefore you can tune the frequency of our qubit. Now, so here you can see an SEM picture of these Josephson junctions, and the line width here is about 100 nanometers. So how do you make that? Well, here at Chalmers and at many labs around the world, we have clean rooms where we have these tools, electron beam lithography machines, which you can use to make these things. It's a bit like how people do computers. You draw a pattern, and you transfer it to, in this case, metal, to aluminum. And then you can make qubits in that way. So now we're interested in how, so yesterday it was also talked about how does light and matter interact. And I think Thomas Ebbesen convinced you that this is important both for everything from the internet to your eye. Light-matter interaction is really important. And so normally, how do you look at that? Well, you have normal atoms and you have lasers, and you shine the laser on the atoms, and then you see what happens. And so typically you use optical frequencies, which amount, so visible light, which amounts to 10 to the 15 hertz. So that's quite high frequencies. But we are using much lower frequencies and much lower energies in general. So we use microwave frequencies, which is more like 10 to the 10 hertz. And we can then build our atoms here, and we can put them in transmission lines. So this is a transmission line. It's essentially a squashed coax. And we put our atom in here, and then we can send in microwaves. We can see how much is reflected. We can see how much is transmitted. And there are a number of interesting things about this system that makes it advantageous compared to using real atoms. So one of the things is that we can really engineer the atoms. We can tailor the parameters of the atom. We don't need to take what nature gives us. We can do it ourselves. The other thing is that we can place this atom everywhere, anywhere on the chip, and it also stays there. You know, if you put a normal atom, it will float away and attach to something else or something like that. So we can put it where we want. Moreover, this coupling between this atom and the light can also be very strong. So as I said, typical frequencies we use is 5 gigahertz. The only drawback here is that we need to cool this down to very, very low temperatures, close to absolute zero. So we work at typically 10 millikelvin or 20 millikelvin. So if you now scatter microwaves off of this atom, what can you expect? Well, if you think of this, you have a plane wave that comes in, you have an atom that scatters, and then you superimpose these two, so you add them together, and what you see is that you have extinction here in the forward direction. And that's precisely what we see. And on this slide here, you see that we have measured the transmittance, so how much comes past the atom, and at low power, and this is really, really low power, essentially nothing comes through. Everything gets reflected. But then as we go up in power, we saturate the atom. The atom can only handle one photon at a time. So if you send 1,000 atoms, 999 are going to pass by, and then the transmission then, of course, goes up to close to 1. We can use this to make toys. So here is a single photon router that we built using these superconducting qubits or artificial atoms. So we have an atom here. We send in a signal from this side. It comes into this roundabout for microwaves, so you can only go one way here. Then it gets reflected here if you do nothing, and then it goes out here. But we can actually modify the atom by sending in a control pulse that is resonant with the first and second excited state, and that modifies the energy levels of the atom so that the atom becomes transparent. So by doing that, we can get the signal that comes in from this side to come out here instead. So we can really make a switchboard on a chip for microwave photons. And the efficiency of this switch is 99% on-off ratio, and the switching time is 10 nanoseconds. So it's a really high quality device. Now, I also want to show you another thing that you can do with these artificial atoms. You can put them on piezoelectric surfaces. How many of you knows what a piezoelectric is? Some. It's something that when you put on a voltage, it actually gets shorter or longer. If you put on an oscillating voltage, it actually oscillates in size. That can create surface acoustic waves that you see here. So these are formerly called Rayleigh waves, but you see that so this is the lattice of a surface, and what you see here is that the atoms are displaced, and it goes like a wave. This is much like ripples on a pond, but it's on a solid surface instead of a water surface. So surface acoustic waves, you see, so if you have an earthquake, that's a surface acoustic wave. That's why you can feel an earthquake far away from the epicenter. So now, how do you actually generate surface acoustic waves, and how do you detect them? Well, what you do is you put two fingers like this, and then you apply a voltage. Then that's going to put some strain in the material. And if you then oscillate the voltage, you're going to have an oscillating strain, and therefore there's going to be a wave that goes out. So to strengthen this wave, you can have more of those fingers, and you can really emit now quanta of sound, which are called phonons, from this transducer here. And also, if the surface acoustic wave comes in here, it can be converted into the electromagnetic domain, and you can read out this. And so, what you realize here now is that the superconducting qubits that we make, they have a capacitance, and we can shape this capacitance in this way. So, in fact, we can combine this transducer and the artificial atom so that the atom talks to sound rather than to light. In fact, we can make the coupling to sound much stronger than the coupling to light. So so we should be able to excite the atom and then listen to the atom when it emits phonons instead of photons. So can we do that? And I wouldn't be here if we couldn't. So here is the experiment we did. So here is our artificial atom that we can then excite with this control. When it's excited, it then, after a while, it decays and it emits a phonon. And the phonons that go out in this direction here, we can pick them up, and we can amplify them, and then we can measure. And that's what you see here. So red means that we have a large signal. Blue means that it's silent. We don't see anything. So the x-axis here is the frequency of the atom that we can change with magnetic field, as I told you before. And this is here on the y-axis is how hard do we drive it, so how much do we excite the atom. And you see here that when we start to excite the atom, we do see signal coming out, which means sound is coming out that we're converting to microwaves, and then we're detecting those. So we can really listen to an atom. Now, so how do you make computation out of this? Well, you make qubits, and it's important that these qubits behave quantum mechanical for a long time. So you talk about coherence times, and they should be long. And for that reason, you need to protect the superconducting qubit from its environment so that it's not disturbed by its environment. So that's one of the reasons that we cool things down to 10 millikelvin. But we also do a lot of other things to protect our qubits from being disturbed. And a bit more formally, there are two types of disturbances. There's one that causes the atom to relax. So if you put in noise, you will you will make the atom relax, and it will emit then a photon normally. But I also showed that you can have a phonon that comes out. Then there's another thing which is called defacing. That's if your levels of your atom, if the energy level is not perfect, if it's wiggling a little bit, then you actually lose information. And that's also something bad. And so what you do is you combine the lifetime here, T1, with the pure defacing, so 1 over this rate. You combine this to a decoherence rate, and that gives you what's called T2. So these are different times that talk about the lifetime of the qubit. And if you look over the last 20 years, the first qubit was 20 years ago, and the lifetime was about a few nanoseconds. Today, they are up to 100 microseconds. And this is something that we can measure here at Chalmers. And an interesting thing is that these times, they actually fluctuate in time. And this is something we need to understand. So if we measure this lifetime over and over again, it actually varies in time. So you can make a histogram of this, and you can see that there's a mean value and there's a spread. And this, we think we do understand how this comes about, but I'm not going to go into detail about that. Then you also need to connect these qubits together. So here's just 2 slides on that. So here you see one of these qubits, and here's the other one. Here you can drive them, so you can manipulate them with these 2 gates. Here you have readout resonators, so that you can read out the state of the qubit. And then in the middle here, you have a coupler, and that can turn on and off the coupling. And you see here that here we have 2 qubits that have relatively good decoherence times, and we can try to couple them together. And this is what you, and moreover, I should say also that one of the important numbers that you look for is the fidelity when you do an operation on a qubit. So this is a number between 0 and 100%, and of course you would like to be at 100%. In these experiments here, it's up to 99.94%. So that's also, so it's as good as what Google is doing. And then you can do these 2 qubit gates. So, and here you see an example of this where we have put one of the 2 qubits in the excited state, and then we can move this excitation back and forth between the 2 qubits. And that you see here when we measure qubit 1 and qubit 2, you see then when this one is blue, this one is red. And then when this one is red, this one is blue. And you can toggle the information between the 2 qubits. And if you do that halfways, then you create a superposition. OK, so this is sort of the upshot of how you do it. And I'm going to let Andreas take over. But I just want to acknowledge the people in the group. This is not the whole group, but it's the people who have contributed to the things that I have shown. So I thank you for your attention.